we will see some problems in scattering. So next problem is example 3. A long single mode fiber has an attenuation of 0.5 dB per kilometer when operating at a wavelength of 1.3 micrometer. When operating at a wavelength of 1.3 micrometer. So the data given was the fiber core diameter is 6 micrometer and the laser source bandwidth 600 megahertz mu. Laser source bandwidth mu is equal to 600 megahertz. Compare the threshold optical power for both stimulated Brillouin scattering and stimulated Raman scattering. Compare the threshold optical power for both stimulated Brillouin scattering and stimulated Raman scattering within the optical fiber cable. So the data given was attenuation in dB alpha dB is equal to 0.5 dB per kilometer, and next operating wavelength lambda is equal to 1.3 micrometer, 1.3 into 10 power minus 6, and fiber core diameter D is equal to 6 micrometer. Fiber core diameter is 6 micrometer and laser source bandwidth mu is equal to 600 megahertz or 0.6 gigahertz. 600 megahertz or 0.6 gigahertz. So what we need to find? We need to find threshold optical power for both SBS and SRS. We know that threshold optical power for stimulated Brillouin scattering is 4.4 into 10 power minus 3, 4.4 into 10 power minus 3 into d square of the core diameter into lambda square of the operating wavelength into alpha dB attenuation dB per kilometer into mu. Mu is the laser source bandwidth. Now substitute the data given in this formula. 4.4 into 10 power minus 3 into d square. D square is nothing but 6 micrometer into lambda square. Lambda square is, now substitute the data given in this formula. 4.4 into 10 power minus 3 into diameter of the optical fiber core 6 micrometer into 10 power minus 6 whole square into lambda square. Lambda is a lambda is 1.3 into 10 power minus 6 into alpha dB attenuation 0.5 dB per kilometer into mu 600 megahertz. Mu is the 600 megahertz. After calculating the threshold power level as stimulated Brillouin scattering is equal to 80.3 milliwatts. After calculating, the stimulated Brillouin scattering is equal to 80.3 milliwatts. Next one is we need to find stimulated Raman scattering. Threshold power threshold power at stimulated Raman scattering, that is equal to 5.9 into 10 power minus 2 into d square into lambda into alpha dB. D square 5.9 into 10 power minus 2 into d square into lambda into alpha dB. Now substitute the core diameter and wavelength and alpha dB attenuation in stimulated Raman scattering. 5.9 into 10 power minus 2 into d square is 6 micrometer square into 1.3 into 10 power minus 6 is the wavelength of the operating wavelength, and alpha dB is 0.5. Alpha dB is 0.5. So PSRS is equal to 5.9 into 10 power minus 2 into d square into lambda operating wavelength into alpha dB is the attenuation per kilometer. So after calculating, we will get 1.3 watts. 1.3 watts is the stimulated Raman scattering. We have already seen absorption, scattering in our previous sessions. Okay, absorption is due to fiber material and scattering is due to structural imperfections. So now we will see bending, which leads to the bending losses, or the losses which leads to the attenuation. So consequently attenuation leads to the signal degradation. Now we will see bending losses. So bending an optical fiber introduces a loss in light power or loss in light beam. These bending losses are also called as radiative losses, and these radiative losses are due to bending of the optical fiber cable. Consequently, it leads to the bending losses. First one is the losses due to curvature. The losses due to curvature and losses caused by the abrupt change in the radius of the curvature are referred to as bending losses. How the bending losses will occur? Losses due to curvature and the losses caused by the abrupt change in the radius of the curvature are referred to as bending losses. If there is a sharp bend, the sharp bend of the fiber causes significant radiative losses, and there is also possibility of mechanical failure. There is also possibility of mechanical failure. Mechanical failure is nothing but breakage of. So there are two types of bending losses. There are the two important types of bending losses. First one is microscopic bending loss. Second one is microscopic bending loss. First one is microbending. The fiber bending with diameters on the order of centimeters or less. Microbending is nothing but it is a fiber bending with diameters on the order of centimeters or less. These are caused by the curvature of the fiber axis. These are caused by the curvature of the fiber axis. This is the representation of microbending loss. This is the representation of microbending loss. There is a sharp bend. You can observe there is a sharp bend in the optical fiber cable. Because of this sharp bend, the radius of the curvature will increase or decrease. The radius of the curvature will increase or decrease inside the fiber axis. Inside the fiber axis. So here at this point, see, we already know that fiber optic cable works on the principle of total internal reflection. Total internal reflection. So at this point, it will not maintain the critical angle. At this point, it will not attain the critical angle, so that it will not attain the critical angle because of sharp bend in the optical fiber cable. There are chances of optical light traveling from core medium to the cladding medium due to not attaining of critical angle condition. Light will get refracted into the cladding medium. So next one is the micro bending. It is a result of microscopic imperfections. It is a result of microscopic imperfections in the geometry of the optical fiber cable. So while manufacturing itself, there will be a bends in optical fiber cable. There will be a bends in optical fiber cables. This also leads to the refracted light through the cladding medium. Refracted light through the cladding medium because of these imperfections. The light is traveling through the optical fiber cable with the principle of total internal reflection. At this point again, it will not maintain critical angle, it will not attain critical angle condition. For that reason, that light will refract it through the cladding medium. Micro bending, the fiber bendings with diameters on the order of centimeters or less. These are caused by the curvature of the fiber axis. So this is the representation, curvature of the fiber axis. And next one is the micro bending, results of microscopic imperfections in the geometry of the optical fiber cable while manufacturing. So this is the macroscopic bending law. As I already told that, so while traveling optical light pulses with the principle of total internal reflection, at this place, because of macro bending, at this place, curvature of the radius, it will not maintain the critical angle condition. So if it will maintain critical angle condition, again it will, as we already know that the manufacturers will give some specifications. So with this critical radius RC is equal to 3 n1 square into lambda, 3 n1 square into lambda by 4 pi n1 square minus n2 square whole power 3 by 2. We know that n1 square minus n2 square is equal to numerical aperture. So numerical aperture is equal to square root of n1 square minus n2 square. Numerical aperture is equal to n1 square minus n2 square. So n1 is the core refractive index, n2 is the cladding refractive index. So lambda is the operating wavelength. RC is the critical radius. Critical radius RC is equal to 3 n1 square lambda by 4 pi n1 square minus n2 square into n1 square minus n2 square whole power 3 by 2. So there are two conditions to reduce this macroscopic bending losses. First one is designing fibers with relative refractive index differences. So it is nothing but difference between n1 square minus n2 square. And second one is operating at short wavelengths possible. So operating at short wavelengths. So when we go for operating with short wavelengths, consequently bending losses, macro bending losses will get reduced. Eventually bending losses will get reduced, so that attenuation also will get reduced. So this is about the macroscopic bending losses. And next one is microscopic bending losses. These microscopic bending losses results from non-uniform lateral pressure of fiber surface. That is nothing but core cladding surface. This is a core cladding surface. Okay, it is this microscopic bending losses results from non-uniform lateral pressures of fiber surface, that is the core cladding interface. This is the representation with power loss from higher order modes, power loss from higher order modes due to micro bends, and power coupling to higher order modes due to micro bending. So this can be minimized by extruding a compressible jacket over the optical fiber cable. This can be minimized by extruding a compressible jacket over the optical fiber cable. Next one is minimizing micro bending losses. So these are the precautions to be taken to minimize the micro bending losses. First one is, while manufacturing the optical fiber cable, precise control of core diameter to be maintained. Precise control of core diameter should be maintained. While manufacturing the optical fiber cable, a precise control of core diameter should be maintained. This is the first one. And second one is, a compressible jacket is fitted over the optical fiber cable. A compressible jacket is fitted over the optical fiber cable so that when the external pressure, we have already seen because of external pressure, there will be a microscopic bending. There will be a chance of microscopic bending. When the external pressure is applied, then the deformation of jacket takes place and there will not be any creation of micro bendings in the core layer of the optical fiber cable. A compressible jacket is fitted over the fiber so that when the external pressure is applied, someone is trespassing towards this optical fiber cable, the deformation of jacket takes place and there will not be creation of micro bends in the core layer of the fiber. Third one is, to avoid deterioration in optical fiber transmission characteristics resulting from microcoupling induced microbending. So mode coupling induced microbending, it is important that the fiber is free from irregular pressures. So next, fourth one. So careful controlling of coating of the fiber optic cable is essential in order to minimize the cabled fiber attenuation. To reduce the fiber optic cable attenuation, the coating of and cabling of the fiber should be carefully controlled. And next one is, fifth one. So furthermore, the fiber cabling must be capable of maintaining the situation under all the strain and environmental conditions. It should sustain all the stress and environmental conditions envisaged in its lifetime. Sixth one is, minimal losses were predicted at operating wavelengths below 1.3 micrometer with a rapid rise in attenuation at wavelengths above 1.5 micrometer. So minimum losses were predicted at operating wavelength below 1.3 micrometer with a rapid rise in attenuation at wavelengths above 1.5 micrometer. So this is about bending loss. Now we will see some example problems in bending losses. Example 1. A multimode graded index fiber has a refractive index at the core axis of 1.46 with a cladding refractive index 1.45. So the critical radius of curvature which allows large bending losses at 8.4 micrometer, which allows large bending losses occur is 8.4 micrometer when the fiber is transmitting light of a particular wavelength. So, determine the wavelength of the transmitted signal. We need to find the wavelength of the transmitted signal. Solution is, so the given data was refractive index of core medium at fiber center axis 1.46 and refractive index of cladding medium is 1.45 and critical radius RC is equal to 8.4 micrometer. 8.4 micrometer. So, we know that critical radius RC is equal to 3 n1 square lambda by 4 pi into n1 square minus n2 square whole power 3 by 2. So, critical radius RC is equal to 3 n1 square into lambda by 4 pi into n1 square minus n2 square whole power 3 by 2. We need to find lambda. So, rewrite this equation to find out wavelength of that transmitted light, particular transmitted light. So, critical radius, I will rewrite this equation again. RC is equal to 3 n1 square lambda by 4 pi into n1 square minus n2 square whole power 3 by 2. So, 3 n1 square lambda is equal to 4 pi n1 square minus n2 square whole power 3 by 2 into RC. So, lambda is equal to 4 pi n1 square minus n2 square whole power 3 by 2 into RC by 3 n1 square. After rearranging this equation to calculate wavelength lambda is equal to 4 pi into n1 square minus n2 square whole power 3 by 2 by into RC by 3 n1 square. Now, substitute these n1, n2 and RC values in this formula. So, lambda is equal to 4 pi n1 square 1.46 square minus 1.45 square whole power 3 by 2 into RC. We know that 8.4 micrometer by 3 into 1.46 square. 3 into 1.46 square. After calculating, we will get wavelength lambda is equal to 818.9 nanometer. So, the wavelength of transmitted light is 818.9 nanometers. Next one is example 2. A multimode fiber with a core refractive index of 1.5, a multimode fiber with a core refractive index of 1.5, a relative refractive index difference of 3%, a relative refractive index of 3%, and an operating wavelength of 0.82 micrometer, and an operating wavelength of 0.82 micrometer. Then find the critical radius of curvature at which large bending losses occur. Find the critical radius of curvature at which large bending losses occur. So now solution is, so the given data is, core refractive index N1 is equal to 1.5 and wavelength lambda is equal to 0.82 micrometer. So relative refractive index is equal to 3%, that is nothing but 0.06. We know that finding the relative refractive index, del is equal to n1 square minus n2 square by 2 n1 square, n1 square minus n2 square by 2 n1 square. So n2 square is equal to, n2 square is equal to, so n2 square is equal to n1 square minus 2 del n1 square, n1 square minus 2 del n1 square. So n2 square is equal to n1 square 1.46 square minus 2 del, that is nothing but 0.06 into 1.46 square. n2 square is equal to 1.46 square minus 2 del, relative refractive index difference, relative refractive index difference 2 del, that is equal to 0.06 into 1.46 square. So n2 square is equal to, so n2 square is equal to 2.25 minus 0.06 into 2.25, 2.25 minus 0.06 into 2.25. After calculating, n2 is 2.115. After calculating, cladding diffractive index we got is 2.115. Now we need to find the critical radius of curvature at which large bending losses occur. We need to find RC. So the critical radius of curvature is given by RC is equal to 3 n1 square lambda by 4 pi into n1 square minus n2 square whole power 3 by 2. So critical radius RC is equal to 3 n1 square lambda by 4 pi into n1 square minus n2 square whole power 3 by 2. So substitute these values n1 square, lambda and n2 square in critical radius formula. So 3 into n1 square is nothing but 2.25 into lambda is 0.82 micrometer, 0.82 into 10 power minus 6, 0.82 into 10 power minus 6 by 4 pi into n1 square. n1 square is 2.25. Core refractive index minus n2 square. Cladding's refractive index 2.115. 2.115 whole power 3 by 2. Whole power 3 by 2. Try to calculate this RC, critical radius. RC is equal to, so after calculating we will get critical radius. RC is equal to, after calculating we will get critical radius. RC is equal to 9 micrometer. After calculating we will get critical radius. RC is equal to 9 micrometer. 9 micrometer. So this is about problems in bending losses.